Hi, and welcome. Let's go ahead and get started. Today, we're going to take a look at section 1.1, which is the section on statistical and critical thinking. So basically what's going to happen in chapter 1, especially in section 1, but in chapter 1, is we're going to kind of lay out terminology and ideas and concepts for what's going to happen in later sections. So we're going to make references to many things that we're going to do later in the course, but just kind of lay out hey, this is what we're going to be doing. This is how it's going to work. These are how these things are connected together. So we're going to take a look at some definitions, some terminologies. We're going to take a look at what we refer to as the process involved in conducting statistical studies, this idea of what does it mean to prepare for, to analyze, and to conclude. The three big steps in looking at analyzing and then making conclusions from data. We'll also talk about the idea of the critical thinking that's going to be involved in this course. Right? It is not just about executing complicated calculations, but it's more about when, why, and how. Okay? All right, so let's start with some terminology. We're going to be using this term a lot, data. And data is going to represent the collection of observations, whether they be measurements or counts or survey responses. So measurements, genders, survey responses, counts of things that we take. So the data will be that collection. So one of my favorite examples is to talk about being the quality control manager at the Coca-Cola bottling plant. And as those cans of Coca-Cola come down the line, they're supposed to have 12 ounces in them, right? And if my job is quality control, one of the things I want to do is I want to make sure those cans have 12 ounces in them. So I'm going to check to see. And when I grab a bunch of cans off the assembly line and I measure how much soda is in those cans, and I get a collection of those measurements, I call that collection my data. And then I use that data to determine whether the Coca-Cola can bottling machine, or in this case, the canning machine, whatever you want to call it, filling machine, is filling the cans correctly. Right? We're also going to use the word statistics a lot. Right? Now, statistics as a field of study, because it has two different definitions, and I'm sorry about that, but it just is how it is. As a field of study is the science of planning studies and experiments. Once you've got it planned, obtaining data for that study or that experiment, organizing, summarizing, presenting, analyzing, and interpreting that data. So you're going to think of statistics as a field of study like biology or chemistry or any other field of study, where in that field of study, our job is to plan how we're going to do things, obtain the data necessary to do that thing, then we'll organize that data, and part of organizing can be summarizing or presenting, so making graphs and tables and charts rather than handing someone a pile of data. Then we're going to analyze that data. That's where we do the math. Okay, so think of the analyzing part as the math. And then the last step is to interpret and draw conclusions. Right? So if we go back to my can example, my Coca-Cola bottling plant, the planning part would be I'm going to go down to the production floor and grab 20 cans to see if the filling machine is filling them properly. The obtaining data part would be going down to the floor and grabbing 20 cans. Then I'm going to take them back to my lab because, I got a lab because I'm cool like that. And I'm going to measure the things that I need to measure for my quality control. So maybe I'll measure the number of ounces of soda in the cans, or maybe I'll put it through some sort of thing that measures the sweetness to make sure there's enough sugar, or I'll measure the caramel colorness of them to make sure it's the right brown for Coca-Cola, or whatever it is. I'll obtain that data. Then I'm going to organize that data. What does organizing the data mean? Well, maybe it means making a table or a chart or a graph and present that data to my boss and go, hey, boss, here's the data I found. Okay? Then I would analyze that data. So let's just go back to is there enough soda in the cans example. I would analyze it and say, okay, am I getting enough? What if the average soda in the can was a little bit less than 12 ounces? Is that okay? Is the average soda in the can a little bit more than 12 ounces? Are morning cans less full or more full? Are afternoon cans less full or more full? And that's going to then lead me to interpret and draw conclusions. Is the machine working properly? Is it working properly in the morning and not in the afternoon when a different operator is there? Maybe it's an operator issue. But that interpreting and drawing conclusions based on that data. And my conclusion could be, this thing is working right. Another word you're going to see a lot is this population word. The population is the complete collection of all measurements of the data that we are being considered. Right? What does that mean? Well, if I go back again to my can example, the complete collection of all measurements would be every single can produced by that machine and how much soda is in every single can. Right? This is the group that we would like to have information about. We'd like to make inferences about a population. We'd like to have that complete collection of data. Rarely is it realistic to have it. I can't measure how much soda is in every single can. It would be too costly. There's just too much time that it would take, too much money that it would take. Even if I could find a way to measure how much soda was in a can without having to dump it out, the sheer volume of cans that I would have to measure would make it impossible. So while populations are what we would strive to gather data from, we rarely ever do. Right? We normally gather data from a sample. And a sample is a subset or a sub-collection of elements or members from a population. So rather than getting all the cans, I might just get some of the cans. Right? And if all the cans we call the population, some of the cans we call a sample. In the rare situation where we actually attempt to gather data from the entire population, we call that process a census. Now, depending on how old you are and how much life you've lived, you might know that every 10 years, the U.S. attempts to do a census, right? Where we try to gather data from every single person who lives in the United States. Okay? Everybody. Census. Some of them. Sample. Okay? All right, let's put this into an example here. Carbon monoxide detectors. There was a journal article recently that talked about the carbon monoxide detector failure rates. And it stated that there are approximately 38 million carbon monoxide detectors installed in the United States. And 30 of them were randomly selected, tested, and of those 30, we found that 12 of them failed to provide an alarm, meaning they didn't work right. Right? Well, what do each of those things that I just highlighted or underlined mean? Well, the 38 million, that's our population. That is all of the carbon monoxide detectors that we wish we could get information about. Obviously, we can't get all of them. So we grab some of them, 30 of them. Since we grab some of them, that's going to be our sample. That's going to be the sum from the population. We didn't get all of them, we got some of them. And then the data that we collected was, do these things work or do they not work? So the data was about 12 of them were bad, which means that, 18 were good? So we got a sample of 30. Our data is that 12 were bad, 18 were good, right? Now the goal here would be to use that sample data as a basis to draw a conclusion about the population. Right? Now I know what you're thinking. And it's what everyone thinks when they first doing statistics. How can 30 be used to talk about 38 million? Because 30 just seems like so few, and 38 million seems like so many. How can 30 predict an outcome for 38 million? Okay? And as we get deeper into the course, we'll take a look at that. And what we'll do is we'll try to quantify whether or not 30 is a big enough sample size to talk about 38 million. And can we say that, well, 12 out of 30, what is that going to be? Let's see, divide both by 3, and we get 4 out of 10, or 40%. Can we say that 40% of those 38 million aren't going to work? Is 30 a big enough sample to make that kind of a statement? That's a bold statement to say that 40%, almost half of these things don't work, right? And as we get deeper into the course, we'll look harder at that question of, hey, is 30 enough? For right now, what you want to take away from this is, if I had just given you this, could you identify what is the population, what is the sample, and what's the data that we collected? Okay? Let's take a look at another example where we actually have to do that. Okay. In a recent survey, 834 employees in the United States were asked if they thought their jobs were highly stressful. Of the 834 respondents, 517 said yes. Okay. What's the population? Well, I got 834 here, but those are the people we actually talked to. So that's not our population, that's our sample. Our sample is the 834 employees. Right? Our population is all U.S. employees. Right? And sorry about that. I have a neighbor who, for whatever reason, thinks it's a great idea to roll around in a golf cart with a speaker. Yay me. Anyway, our population is everybody who's an employee. I can't talk to everybody and ask them, is your job stressful? It's just not going to happen. I mean, we're talking several 100 million people there. So I talk to some of them. The sum that I talk to is my sample. And what's the data that we collected? Well, the data we collected is the 517 yes answers. And then what is 834 less 517? Make that a 2, make that a 4, make that a 7, make that a 1. Make the 317 no answers that we got out of our survey. So we have a population. That's the people that we want to make inferences about. That's the thing where in the end I want to go, hey, does this accurately predict that? Can I say that 517 out of 834 said yes? So that means that whatever percent that is, and I'm going to guess that's about 60%. Like 60% of the people think that that's a yes. Let's check that. What's 517 divided by 834? Hey, 62%. So can we say that 62% of employees think their jobs were stressful? Is that the prediction we can make? Is that the inference we can make? Okay. And again, when we get a little deeper into the course, we'll look at whether or not we can consider this an accurate value or how accurate we can consider that. Okay. All right. So statistical and critical thinking as a process. So let's take a look at the process that we'd want to go through if we were going to develop. Right? When we're looking at data, that's been gathered for us, or when we're looking to gather our own data, the first step we want to take a look at is just preparing what we're going to be doing here. So what's the context of this? What do the data represent? And then what is the goal of the study? So if I'm reading someone else's work, if I'm reading someone else's statistical information, I want to know what's the data? What question was asked? How did they get it? What's the goal of the study? Right? What's the source of this data? Right? Did it come from a special interest group? Was there pressure that was put on them to obtain results? Right? Back in the day, and this is kind of old, but it's still relevant. Back in the day, the big tobacco cigarette manufacturers put out lots of studies that said smoking did not cause cancer and it wasn't bad for your health. Do you think that maybe there was a special interest that put pressure on those results? And so a good question to ask is, where did this data come from? How did they get it? Who paid for this? That kind of thing, right? Another thing you might want to ask yourself is, how did they get the data? What was the method that they used to collect the data? Was the data collected in a way that was some way unbiased, or was it possibly biased? Right? Because we don't want biased data, right? So how did they get their data? How did they collect it? Okay. All right, so let's say that you've gone through that and you accept that the data is good, it is unbiased, there was no pressure. Next thing you want to do is you want to analyze that data. Whoop, I don't want that one. I wanted a highlighter, sorry. You want to analyze that data. Now, analyzing the data falls into a huge category. It could be something as simple as just taking a look at a graph of the data, but even there's lots of different graphs. We could do an XY graph, we could do a circle graph, we could do some sort of bar graph, we could do some sort of dot plot. There's lots of different ways to graph data, but the idea behind graphing data is a big pile of data is ugly to look at. Can I make it into a picture that tells the story that I needed to tell, that explains the relationship between things or shows how the data is distributed in a way that's easier to digest as a reader, right? Once I've got my data, though, then I start to explore the data. And by exploring the data, I just want to take a look and see if there are things in there that jump out at me. Are there any of these guys, things we call outliers? And what outliers are is outliers that just look either too big or too small, so very far away from most of the data. Like if I had a data set, and if I go back to my Coca-Cola cans, right? I know that my cans are supposed to have 12 ounces in them. And I've got a data set, and when I measured it, all of my data is in like the 11 to 12 to maybe 13 ounce range, right? But I've got one data point that's 4.6 ounces. Okay? I would look at that 4.6 and I would go, what are you doing there? You're really far away from the rest of the data. Are you an outlier? Are you supposed to be there? Is that a legitimate measurement? That kind of thing, right? The next thing I want to do is look at how can I summarize the data? What important statistical summaries can I do? And we'll dig into this in chapter 2 and chapter 3, right? How's the data distributed? Is it evenly distributed? Is it heavy on one side? Is it heavy on the other? Are lots of my soda cans in the below 12 range and only a few in the above 12 range? Where is the data heavy? Where is the data light? Right? Is there missing data? Are there gaps in the data? And does that matter? Right? If you're doing a survey, did you have people that refuse to respond to you? Because that can be a thing too. If people just say, hey, I'm not talking to you, does that matter? Right? Also under analyze is where we start doing statistical methods, where we use technology to crunch the numbers, so to speak. Right? Crunching the numbers, doing the calculations. Okay? I want to highlight an important word here, technology. As I discussed in our welcome video, that's where we're at that TI-84 graphing calculator is going to come into play, okay? Because it is going to be doing the number crunching for us. We might have to take that data and put it into the calculator, but once it's in the calculator does all the work for us, right? Last step is the conclude. Do your results have statistical significance, right? And what does statistical significance mean? Well, statistical significance is the idea of, could your results have happened by chance? And if there's a low probability that your results happened by chance, then we would say that you are statistically significant. If there's a high probability that chance could have given you that outcome, you're not significant, right? All right, so let's look at an example here. This is from Florida. This is about the relationship between pleasure boats, which basically just means, not work boats, not like the boats that carry stuff from China across the ocean, and manatee fatalities. So manatees are those sea cows, those great big mammals that live down there. The fatalities, specifically the fatalities from boat encounters. Now, boat encounters is a really generous way of saying people ran into the manatees with their boats, and unfortunately the manatee died. All right, so here we got some data. Someone collected this data. I've got one row here that measures the number of boats in tens of thousands, so that 99 right here in that first cell isn't 99 boats, it's 99 10,000s. What the heck does that mean? Well, that would mean 99 times 10,000, or 99 with 1, 2, 3, 4 zeros after it, 990,000 boats, right? So since they're measured in 10,000s, you multiply by 10,000 to get the actual number, right? And then below that we have manatee fatalities, and the manatee fatalities are just in units, so that 92 there does mean 92, right? All right, now the way this data is presented, what the goal would most likely be, the format of that suggests that we're trying to determine whether there is a relationship between how many boats there are and deaths of manatees. Maybe we're supposed to suggest that more boats would mean more manatees would die, or less boats would mean less manatees would die, right? So that's the context that we're looking at here. The data, the source of the data, is the Florida Department of Highway Safety and Motor Vehicles, because boats fall under them for whatever reason, and the Florida Marine Research Institute. Now, both of those appear to me to be reputable and acceptable places to get data from. I don't think that either of them would try to bias the data, push it in one direction or the other. Okay? And since the data appears to come from official government records, well, then we're going to assume that it's reliable and that the method used to calculate it was a sound method to gather this data. Okay? So it looks like we got some good data. Now we move on to the analyze part, where we would try to graph this or explore the data. Right? Now what I'm thinking is, since we're trying to develop a relationship here to show that more boats means more fatalities, I'd probably want to try to graph this stuff on a horizontal XY kind of thing, where one axis could be the number of boats and the other axis could be the number of, and I'm just going to say deaths for two reasons. One, because I don't want to write manatee, and two, because I don't remember how to spell manatee. And what I would be expecting to see is something that did this to imply that if the number of boats increases, the number of manatees increase, or manatee deaths increases. But maybe it'll look like this. And I'll have some sort of a curve that does this to measure what's going on there. Or maybe the graph would end up, whoops, I don't want that. Maybe the graph would end up looking like this and curving up. And then we'd have some sort of a parabola that would measure it, right? But until I graph that data and look at what's going on there, I don't really know whether it's kind of a linear, a line, or maybe some sort of an exponential, or maybe some sort of a quadratic, or some other relationship. I just wouldn't know until I was able to get there. Right? All right, I'm going to stop this first video here. We're already about 23 minutes. I try to keep them to 20 minutes or less. It just uploads faster and that sort of thing. So we'll come back, and in part 2, we'll pick up right here about graphing the data.